Welcome to this Yokogawa e-learning module. This module covers the digitalYEWFLO basic key features. When you have completed this module, you should understand sources of noise in the plant, procedures for signal processing, spectral signal processing, SSP, adaptive noise suppression, ANS, spectral adaptive filter, SAF, multivariable, saturation steam measurement, gas measurement, and liquid mass calculation. Let's start by looking at sources of noise in the plant. Various noise sources exist in the factory, and a Vortex Flowmeter is installed in heavy-duty conditions. Motor, power generator, compressor, pump, engine, and so on. These devices generate vibration. They create fluid vibration noise and mechanical vibration noise in the plant. Transformers generate electromagnetic and static noise. Inverters, PLCs, relays, SSRs, and many other electronics generate electromagnetic, static, and conduction noise. In the actual plant, various noise sources affect the correct operation of Vortex Flowmeters. Vortex Flowmeters must be highly noise and vibration tolerant. The digitalYEWFLO performs accurate measurement in electrically noisy environments. It is EN 61326-1 and EN 61326-2-3 certified. And the digitalYEWFLO's SSP technology enables accurate measurement in mechanically noisy environments. These are key features of the digitalYEWFLO. This section explains the procedures for signal processing. Here is a block diagram of the digitalYEWFLO. All signal processing is digital. Adder, filter, Schmidt trigger, and other functions are implemented on a gate array. This reduces parts, cost, and size, and increases reliability. Let's look at the procedures for signal processing. Two piezoelectric sensors generate electrical charge by lift force. A charge converter converts the electrical charge to voltage, and an AD converter converts the analog signal to digital. Spectral analyzers 1 to 3 are made up of a number of low-pass and high-pass filters. They divide the vortex frequency band to a number of subbands. Digitized signals are converted to signal amplitudes by subbands. An adder provides output of AD with a noise ratio set by the CPU. The spectral analyzers detect the signal band and set a suitable band-pass filter. This graph shows band-pass characteristics of a band-pass filter. It has 6 separate bands. The output signal of the band-pass filter is converted to pulses by a Schmidt trigger. Next, the CPU calculates the frequency and flow rate. Finally, an analog signal and status are output. This section explains SSP. SSP means Spectral Signal Processing. The digitalYEWFLO has a unique digital signal processing technology called Spectral Signal Processing. SSP consists of the adaptive noise suppression, ANS, and the spectral adaptive filter, SAF. ANS suppresses vibration noise, and SAF separates the vortex signal and vibration noise. This section explains ANS. ANS means adaptive noise suppression. It is technology that is used for mechanical noise suppression. This picture shows the construction of detector portion. The shutter bar assembly of the digitalYEWFLO is using 2 piezoelectric sensors. This picture shows the output of the upper and lower piezoelectric sensors. The 2 sensors generate phase signals that are opposite from one another. The noise caused by their vibration is superimposed on the signal at the same time. This picture shows the front, side, and top view of the body and output signal. Fluid flows in the body. The shutter bar generates the vortex at its edge. The vortex brings lift force to shutter bar, and sensors generate electrical charge by the lift force. The shutter bar generates vortices alternately. The vortices apply lift force to the shutter bar, and sensors generate electrical charge. Let's look the details of the ANS. Noise is superimposed on the waveform of the sensor output. Here is an actual waveform from the sensor. Small waves are noise. Large waves are vortex signal. The phases of upper and lower sensors' signals are reversed. In this case, the upper sensor's signal value is 3 and its noise value is 1. The lower sensor's signal value is 1 and its noise value is 3. If the noise values are the same, they cancel each other out because the polarity of waveforms are inverted. However, in this case, the upper sensor's noise value is 1 and the lower sensor's noise value is -3. This is 1/3 of the lower sensor's noise value. After processing, the upper sensor's noise value is 1 and the lower sensor's noise value is -1. Adding cancels them out. Here is a waveform with the upper and lower sensors' output. Here is the resultant waveform after processing. Noise value is 1 - 1 = 0. It was balanced out by processing. The signal value is 3 - 1/3 = 1/3. The CPU continuously calculates the noise ratio. This is the working principle of ANS. This section explains SAF. SAF means Spectral Adaptive Filter. It is a technology for noise detection and calculation of the signal-to-noise ratio. Let's look at this in detail. Here is block diagram of the digitalYEWFLO. Spectral analyzers 1 and 2 analyze the frequency spectrum and output signal levels for each band of the bandpass filter. The CPU receives and calculates the spectral analyzer's output. It detects noise in the specific bands, calculates the noise ratio, and sets the noise ratio on the adder. This graph shows distribution of the signal level output on Spectral Analyzer 3. The sensitivity curve for the vortex frequency is known. The judgment criteria for the vortex signal are the signal level over the sensitivity curve and the largest level band. In this case, SB4 is over the sensitivity curve. This band is determined to be signal. SB2 is larger than SB4, but the signal level is lower than this sensitivity curve. It is determined to be noise. Finally, a bandpass filter is set on the vortex signal. The vortex signal goes through the bandpass filter, and noise in other bands is suppressed. This section explains multivariable. The digitalYEWFLO multivariable type has a built-in temperature sensor in the shutter bar. The sensor is PT1000 equivalent Class A. It can measure temperature accurately for steam, gas, and liquid. Flow rate measurement and temperature sensing in one body enables the function, mass flow rate by temperature compensation. The types of fluids are saturated steam, gas, and liquid. Superheated steam measurement requires a pressure sensor and flow computer. This section explains saturated steam measurement. Let's learn about saturated steam measurement. Saturated steam measurement is mass flow measurement. Mass flow is the volume of flow times density. Density can be determined by temperature. Therefore, we can measure the saturated steam by volume of flow and temperature. The digitalYEWFLO measures volume of flow. A built-in temperature sensor measures temperature, The saturated steam curve is in the software. The density is determined by the saturation steam curve. Therefore, we can measure saturated steam by using only the digitalYEWFLO. This section explains gas measurement. This graph shows volume versus temperature in gas. The gas volume is proportional to the temperature. If we need units of volume at a standard or normal condition from operating condition, we should standardize or normalize it through temperature compensation. This formula shows volume unit by standard or normal condition. The digitalYEWFLO can measure gas temperature with a built-in temperature sensor, and it can standardize or normalize values with temperature compensation. Therefore, the digitalYEWFLO can measure volume units based on standard or normal conditions. In this case, the digitalYEWFLO uses fixed pressure values for the calculation. If we need accurate measurement of gas flow, we should use a pressure sensor and flow computer to do the temperature and pressure compensation. This section explains liquid mass calculation. Let's look at liquid mass calculation. Mass flow equals density times the volume flow rate. The actual conditions in the plant, such as process temperature, pressure, and flow rate, are frequently changing. This graph shows the density versus temperature of a liquid. As the temperature rises, the volume increases and the density decreases. This means that the volume flow changes with temperature. If we measure liquid mass flow, we can compensate the volume flow. The density of the liquid is compensated per the measured temperature value. This formula shows the liquid mass calculation of the digitalYEWFLO. Precise temperature coefficient values of the liquid are important for accurate mass flow measurement. Next is a summary of the key features in this presentation. Here is a summary of what we discussed in this module. We looked at sources of noise in the plant, some noise suppression technologies, and a technique for calculating mass flow. This concludes our module on the basic key features for digitalYEWFLO Vortex Flowmeters. For more information or to contact us, please visit our website and official channel on YouTube. Thank you.